Once we've set up our hypothesis test, there's three ways that we can make a conclusion about whether we reject or fail to reject the null hypothesis. The first way is called the critical region method. So what we're going to do is we're going to figure out what the rejection region is. We're going to calculate our test statistic, either based on our standard normal z or our student's t-distribution t, and then we're going to look at, does it fall into the rejection region, meaning that we conclude that we reject the null hypothesis, or does it fall in the fail to reject region, which means that we would fail to reject the null hypothesis. The second method is going to be using p-value, and we're going to be doing a comparison of our p-value with our level of significance alpha to determine whether we reject or fail to reject the null hypothesis. And the last method, which we're not really going to use very often, is the confidence interval method, where we're going to look at the confidence interval, just like we did in Chapter 6, and if our value of our test statistic falls within that interval, that would mean that we failed to reject, and if it falls outside of it, it means that we would reject. So let's first start by looking at the critical region method and how we would actually find this critical region. So if we have a normal distribution or a student's t-distribution, but let's say in this case we have a normal distribution, and I'm doing a one-tailed test. Actually, let's start with a two-tailed test. I would need to figure out where half of my alpha is to the left, half of my alpha is to the right. And this is going to be related to what we did when we were doing confidence intervals. We would need to figure out what critical value would cause this interval to exist. So if we had an alpha of, let's say it's 0.05, then we would have 0.025 to the right and 0.025 to the left. So the z-value that's going to make this true is the z-value that, in our case, we're looking at our table of probability to the left of a specific value. If this is 0.025 and this is whatever's left and 0.025, this means that we know that how much has to fall to the left of this value. Well, if this is 0.025 or 2.5%, we know then that this needs to be 0.975. So we would go into our table and we would find what z-value is associated with 0.975. So we go down here to 0.975 on the table, and this gives us a value of 1.96. So in this case, our z-value would be equal to 1.96, and our negative z-value, so this would be our rejection region left, would be at negative 1.96. Now these z-values, I've been calling them the z-critical value because they're the value at which you go from the fail to reject region, and once you cross that threshold, you are now in the rejection region. In this case, because it's two-tail, I can reject it either in the positive direction or in the negative direction. So if I get a value that is less than negative 1.96, let's say negative 2.33, it falls in the rejection region. If I have a value that falls above 1.96, let's say 2.78, this would fall into my rejection region. But anything that falls between negative 1.96 and 1.96 would fall in the fail to reject region. Now, what happens if we have a one-tailed test? So still using alpha equals 0.05, I'm now going to have all of this just in this rejection region if I'm doing a right-tailed test, meaning that this area of this rejection region is 0.05, meaning that I would need the z-value that accounts for 0.95 of the data to the left. So in this case, I'm going to look at my table and I'm going to find 0.95, which the closest value is actually between these two. It's going to be 1.645. In which case, this means that anything that is above 1.645 falls in the rejection region. Any test statistic that is below 1.645, whether it's positive or negative value, this would be in the fail to reject region. Now, if we compare both of these, you'll notice that both of them had an alpha of 0.05. But I actually have a much higher threshold in the positive side when I'm doing a two-tailed test versus a one-tailed test. So whenever you're doing these tests, you have to actually make sure that you're doing the correct test, because if you don't, you actually could have this region in between where a two-tailed test would say that you reject the null hypothesis, or rather you have a one-tailed test that says you reject the null hypothesis, but it's not into the rejection region of the two-tailed test. So anything that we've done here with the right-tailed test would be exactly the same for a left-tailed test. If we had a left-tailed test, if we have some alpha, again, let's do 0.05, it would be however much, we have 0.975 is to the right of this, And because of symmetry, we know that this is the same thing as the positive side. Everything to the left is 0.95. This would actually be the same value as the positive test, except for now our z would be equal to negative 1.645. Now, you could also do this if you wanted to. If you had a z-table that is looking to the left of negative values, you could then just look up what value has 0.05 to the left of it, and it would work exactly the same way. Now, this is the idea, though, that comes out from the rejection region method. This, though, is actually the reason why we could also use the confidence interval method when we have a two-tailed test. Because if this value looks familiar, it's because when we did a confidence interval, it's the same value that we had for the confidence. Because if you remember, c was equal to 1 minus alpha, or alpha equals 1 minus c. Meaning that if alpha is on the outside, this c is on the inside. Meaning that you're actually finding the outside of your confidence interval. So the confidence interval method is basically just saying, okay, this is the area of the fail to reject, so anything that falls outside of my confidence interval falls into the rejection region. But you can't really do this and have reliable results if you were having a one-tailed test, because as we mentioned previously, a two-tailed test, let's say it goes to here, is going to have two places where it can fail. One, I have this region right here where it would fail, or we would reject it for a one-tailed test, but we failed to reject it for a two-tailed test because it falls into our confidence interval. This means we would get the incorrect answer even based on the data that we have. Also, I could have data that falls to the left of this confidence interval, which would also cause me to reject it, even though I'm only doing a right-tailed test. I can only reject it in the right direction, and yet I can actually reject to the left if I did a confidence interval method. When we're doing a hypothesis test, we specifically want the probability for rejecting the null hypothesis to be as small as possible because we want to limit our type 1 errors. We want our type 1 error to be small. The most common level of significance that we'll use is alpha equals 0.1, alpha equals 0.05, and alpha equals 0.01. So alpha equals 0.1, alpha equals 0.05, and alpha equals 0.01. And for each of these, if we have an alpha of 0.1, this is the same thing as saying a confidence of 0.9 if we're doing the two-tailed test. If we have an alpha of 0.05, this is the same as saying confidence 0.95. And if we had alpha as 0.99 or 0.01, this would be the same as saying confidence level of 0.99 for a two-tailed test. And we actually already talked a little bit about what these values would be. For a one-tailed test, you're going to have different values than if you have a two-tailed test. So then you actually have to consider what are the types of tests you're doing. So in this case, we might have alpha equals 0.1, alpha equals 0.05, alpha equals 0.01. And then what type of test is it? Is it a right-tail test? Is it a left-tail test? Or is it a two-tail test? And each of these are going to have a different critical value or critical values of z. So let's quickly figure out what each of these are using our z table. So we actually already looked at what our alpha was when we had, for a right-tailed test, when we had an alpha of 0.05. We just looked at what would have 0.95 of the data to the left, which we said was going to be equal to 1.645. Which means that our left-tailed test would be negative 1.645. And these are for our z values. If our alpha is 0.1, this means that we have 0.9 to the left of it. So we would go and find where 0.90 is, and this would give us 1.28 and negative 1.28. And then finally, if we have an alpha of 0.01, this means we have 0.99 to the left of it, meaning that we are going to have a value of 2.33 and negative 2.33. Now, if we have a two-tailed test, we have to take into account that we're looking at however much is not included in this alpha to the left. So if we have an alpha of 0.1, this means that half of this would mean that we have 0.05 to the right, meaning that we're looking at 0.95, which we actually just said was going to be plus or minus 1.645. For an alpha of 0.05, it means we have 0.025 above, which means we're looking at 0.975, which we said was going to be equal to 1.96. And finally, if we have 0.01, to half of it to the right, half of it to the left, this means we have 0.005 to the right, meaning we need to find the value that has 0.995 to the left. So we go to our table, we find 0.995, and we get that it is equal to 2.58. So plus or minus 2.58. Now from there, as long as we're using a standard normal distribution, and if we're using one of these most common alpha values, then we have our critical values that will determine our rejection region, whether we have a right tail test, a left tail test, or a two tail test, and whether we're using alpha equals 0.1, alpha equals 0.05, and alpha equals 0.01. Now, if you have an alpha level that is not one of these, you would find it the same way. You would figure out if you're doing a one tail test. If it's a right tail test, you just figure out what alpha is, and then you're going to be looking up on your graph what is the value of z that has 1 minus alpha to the left of it. If you're doing a left tail test, you just use symmetry, figure out what the value is to the left of a positive, and then just make it the negative z. And if you were doing a two tail test, you're going to have two z critical values, where this is going to be alpha over 2. This is also going to be alpha over 2, in which case you want the value that is going to be 1 minus alpha over 2 to the left of the positive z. And then you just have to know that you also have a negative z critical, which is the same value, just negative. If you're using a student's t-distribution, which is on the back side of my chart here, it's going to be similar, except for it's going to be a little bit different because we're going to have to actually take into account what are our degrees of freedom. The student's t-distribution is going to be based on, if you look at this chart here, now notice on our graph here, we have one tail is the top row, two tail is the second row. So you're actually going to determine which column you're in based on whether you use the first row and you find your alpha level. So for example, here's alpha 0.01. And if I were to do two tail, alpha equals 0.01 would be right here. So you'll notice that you first need the first or second row based on whether you're doing a one or a two tail test. If you're doing a left tail test, you just use the same values for the right tail test, but make it negative. So let's say you're doing a one tail test. Let's say that we have a right tail test where we have alpha is to the right here. This is our rejection region. This means that if we want to find the value to the left for our t critical, it is going to be based on our degrees of freedom, n-1, and in this case, it's going to be based on our alpha level. So we go to one tail test, which is the top row. If we have an alpha of, let's say 0.01, and we have an n of, let's say 20, this means our degrees of freedom would be 19. So we go to one tail test, we go over to 0.01. On the left side, we go down to 19 for degrees of freedom of 19, and then we see where those two meet. So 0.01, 19, we get a critical value of 2.5395. This works exactly the same way if you're doing a two-tail test, except for then you would use the second row to find where your alpha level is. Once you've figured out this rejection region, whether you're using Z or you're using T, now we need to figure out what is our test statistic. So our test statistic when we're using Z is going to be based on our standard normal, which is going to be x bar minus mu over sigma divided by the square root of n. You will calculate your test statistic and you will see, does it fall into my rejection region or does it fall into my failed to reject region? If you're using student T, then your T test statistic would be x bar minus mu over s divided by square root of n. But in the end, the calculation is basically the same. You're looking at how far is the point estimate that you got for the parameter based on the actual parameter. Now, again, as before, we don't know what the true parameter is. So what we're going to do is we're just going to be assuming that the null hypothesis is true. So, is true. Because what we're doing is we're kind of going off the statement of if this null hypothesis were true, does it make sense that my data is so far away from what would be expected? And that's actually what we're looking at when we do a hypothesis test and we have this level of significance. If I have a level of significance of 0.05, this means that I would expect, if I'm doing a right tail test, that 95% of the time, if this null hypothesis were true, because remember this mu is based on my null hypothesis, then this test statistic out here on the far right should only occur naturally 5% of the time, which is not very likely. So this actually means that the smaller my alpha is, the harder it is to reach that threshold. Because if my null hypothesis were true, that means I would only expect it to fall outside of, let's say alpha is 0.01, I would only expect it to fall outside that value 1% of the time. So if my data happens to be that 1%, that either means one of two things. Either I got really lucky when I did my data collection and I happened to get that 1%, or my value fell outside of it because maybe this null hypothesis mean is actually not true. So when we're doing our test statistic though, we're still assuming that it's true because we're trying to show that the evidence from our actual data is enough to show that this probably isn't likely. So we're kind of starting with the statement of assuming that the null hypothesis is true, what do I get, and does it make sense then that the null hypothesis would be true? Let's go back to the examples we did when we first introduced hypothesis testing and actually do the next steps now to see what would happen. So we're going to start from the beginning and we're going to go all the way through doing our critical region method to determine whether we reject or fail to reject the null hypothesis. So the first example says, an SAT tutoring center claims that the average math scores of their students in the SAT is 500. Consider a small sample of 20 students. The sample mean of their scores is 521.5. Previous records show that the standard deviation is 120.5. At the 5% level of significance, do we have sufficient evidence to prove that the average math score and the SAT are different? So a couple of things here. First thing I'm going to do, I'm going to write down my given information. So given that I have some specific information. So the first thing it's given is we have a small sample of 20 students. So n is equal to 20. We have a mean, which is from our data, of 521.5. So x bar equals 521.5. Previous records show the standard deviation is 120.5. So this previous record means that this standard deviation did not come up from our data, meaning that we're taking this as an assumed sigma or standard deviation is known. So in this case, our standard deviation is 120.5, and then we have an alpha of 0.05. Now let's set up our null hypothesis and our alternate hypothesis. So our null hypothesis is that initial claim that the company made. Mu is equal to 500. My alternate hypothesis, because we just want to show that it's not true, we're going to say mu is not equal to 500. Now, before we actually go on to finding our critical region or finding our test statistic, we first need to see which distribution we're in. So now what we're going to do is we're going to check our assumptions. So in this case, the first assumption is sigma known. Well, in fact, for us, sigma is known because we know that we had this value from outside of our sample, meaning we didn't calculate it, so we're treating it as sigma. And if we did n, we would say that n is equal to 20, which is not greater than or equal to 30. So it fails this assumption. But if you remember, when we're doing a hypothesis test, our assumptions of sigma known or n greater than or equal to 30, only one of them has to be true. So based on this, we are going to use z. So now that we know that we're using the standard normal z, we can figure out what is our rejection region. So if we have our standard normal, and we are doing a two-tailed test, right? Because we're doing our alternate hypothesis is mu is not equal to 500. This means that we will have a negative z critical value to the left, a positive z critical value to the right, and we know that the area of these two together should be alpha. So that means that this is going to be alpha over 2, and this is going to be alpha over 2. So if we have alpha over 2, which in this case is going to be 0.025, we know that we need the z critical value that has 0.975 to the left. So again, we can go to our table and we can find where 0.975 is, and this would give us a value of 1.96. So we know that this critical value is equal to 1.96. and this critical value is negative 1.96. And we will reject any test statistic that falls outside of this range. So this is our rejection region. So now it's time to figure out, do we reject or fail to reject our null hypothesis? So what we're going to do is we are going to find our test statistic, which was z equals x bar minus mu over sigma divided by square root of n. Well, in our case, x bar is equal to 521.5 minus, remember, our null hypothesis we're going to treat as our mu. So this is going to be minus 500 divided by sigma, which is 120.5, divided by the square root of n, which we said was 20. So then doing this, we are going to get a test statistic of 0.8. So now if we were to look at this normal distribution here, where would this 0.8 fall? Well, if this is centered at 0, because this is a standard normal, this means that this would fall somewhere to the right of 0, but not beyond 1.96. So this means this falls in our fail to reject region. So based on this hypothesis test, we do not have enough evidence to reject the null hypothesis at a level of significance of 5% or 0.05 alpha. For the second example, we have an SAT tutoring center claims that the average math scores of their students on the SAT is 500. Consider a small sample of 20 students. The sample mean of their scores is 480 with a standard deviation of 120.5. At 5% level of significance, do you have sufficient evidence to prove that the average math score in the SAT are less than 500? So again, we're going to start by writing down our given information. So given, we have a small sample of n equals 20. We have x bar equals 480 in this case. Now, the next part is our standard deviation. Now, the way it's written is that we have a sample mean of 480 with a standard deviation. This is implying that we actually calculated this from our sample. So in this case, we have S equals 120.5. And then, of course, our alpha is 0.05. So now what we're going to do is we're going to set up our null hypothesis and our alternate hypothesis. So our null hypothesis is that initial claim, still that the mean mu equals 500. And what we're testing is that it's less than 500. So in this case, we're doing a one-tail test to the left. So we're doing a left tail test. Now, before we move on, we need to figure out which distribution we're using to do this hypothesis test. So we check our assumptions. So the first assumption is sigma known? Well, in our case, sigma is unknown because we just said that we found it from our sample, meaning that it fails this. And our n is equal to 20, which is not greater than or equal to 30. So it fails this as well. If both of them fail, then this means that we would use t. So now let's figure out what our rejection region is. We're doing a one-tail test, and it's a left-tail test. So if we were to draw out our student t distribution, again, centered at 0, we know that we should have some t critical value where 0.05 is to the left of this value. So the way we find this is, again, our t table only has the positive values. So what we're doing is we're finding the values to the right of what the t critical would be on the right, and we're just putting the negative on it. So we're going to go to the top, and we have a one-tail test. We have an alpha of 0.05. We have degrees of freedom of 19 because it's 20 minus 1. So we go to 0.05, degrees of freedom of 19, and we get 1.7291. But because this is a left tail test, we know that this has to be the negative value. So this is negative 1.7291. So this is our rejection region. Anything that is less than that would fall into our rejection region. Now we need to find our test statistic to see if it falls in the rejection region or the failed to reject region. So our test statistic, t is going to be equal to x bar minus mu over s over square root of n, which, again, same basic calculation, but because we know we don't have sigma and we know we're using student t, we're using s. So in this case, our x bar is going to be based on our given information, which means that we have 480 minus the initial claim of 500 divided by our standard deviation s 120.5, divided by the square root of n, our sample size, which is 10. Now this is going to give us a test statistic of negative 0.74. So if we were to figure out where this falls on our distribution, it falls to the left of 0, but it does not go beyond negative 1.7291, meaning that this falls into our fail to reject region. So in both of these examples, we did not have enough evidence to reject our null hypothesis at our level of significance. For the first one, it was alpha is 0.05 for a two-tailed test. For this one, it is alpha is 0.05 for a left-tailed test. So up until this point, we've only really looked at one way to do the hypothesis test, which is the critical region method. So the critical region or rejection region is just the range of values where our test statistic can fall for our null hypothesis. And if it falls in that rejection region, we would reject the null hypothesis. If it does not fall into that region, or regions if it's two-tail, we would fail to reject our null hypothesis. When we're actually creating our rejection regions, it's going to be based on the type of test we're doing. Are we doing a left tail, a right tail, or a two-tail test? If you look at this slide, this kind of just gives you an illustration of what the rejection regions would look like based on your alpha. So the first one on the bottom left is a left tail test, and our rejection region is on the left. The second one in the middle is a right tail test, so our rejection region is on the right. And the last one is a two-tail test where we have a rejection region both above and below. And then, of course, we have to figure out what is the actual critical value that is the threshold when you go from the fail to reject to the rejection region. So for the standard normal, you just have, especially if you're using one of our main alphas of alpha 0.05, 0.01, or 0.1, then we would have some set specific values, which you can see in this little subtable here. If we are using a different value, you would have to go to your actual full Z table, and you would have to figure out from that. Next to this, you'll see an example of our student T table. And you'll notice that only certain blocks are visible. And this is because generally, if we're still using alpha of 0.1, 0.05, and 0.01, then this means that on the top row, which is your one-tail test, these would be the columns of interest. The first column, the second column, or in this case, the fourth column. If you're in the second row for a two-tail test, then in this case it would be the second column, the third column, or the fifth column. And basically what's happening when you're doing this, if you actually look at it, is that all of your T values, your alpha values on the T table, are just offset from each other. And it's because it's taking into account what we did when we found our rejection region for that critical value, is that if I have a two-tail, I just know that I'm only taking half of it, so it's shifting over by that amount. And then what you do is you figure out which of those two rows you're in, which column it caused you to be in, to use, and then you go down the left side, you find your degrees of freedom, you see where they intersect, and that gives you your critical value. If it's a left tail test, remember to make it negative. If it's a right tail test, you can use the number in the chart, and if it's two tail, you have to use positive and negative because you have two critical values where if you go beyond it, you reject the null hypothesis. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.